My contribution to the project was to use Gaussian mixed models for cluster analysis, i.e. unsupervised learning. So our motivation for doing this is that the housing prices can be thought of as being determined by the interaction of many different factors. So things like the size of the house, the number of rooms, the size of the kitchen, and then features of the neighborhood. So how close is it to shopping? How close is it to cultural sites? How industrialized is the neighborhood? Information like that. And we also, when we were researching possible applications of Gaussian mixed models, we did see that they had been used in the past to look at housing data. So it seemed like a plausible application. Our data came from Kaggle. It's from the Russian housing market contest they currently have going on. Roughly 19 categorical attributes and then 118 numeric attributes, and that's after we removed a lot of highly correlated columns. So they're originally closer to 300 attributes. Most of the attributes don't pertain to the houses themselves, but pertain to the neighborhoods. So information like how green is the neighborhood, how close is it to shopping, how close is it to offices, information like that. One feature of the data is that it was highly correlated. We had a lot of 95 plus correlations and a lot 70 plus. This actually, in this instance, was useful because it meant that we could use PCA to transform the data, and also we could use certain attributes as representative of other attributes if we wanted to. Because Gaussian mixed models, the more attributes you add to them, the slower they perform, and memory and computation time was a serious issue with our modeling. This is a distribution. These are some of the distributions of the data we elected to use. As you can see, they're not perfectly normally distributed. Some of them might be better defined as exponentially distributed. And we considered using a log transformation on this data, but opted not to, because when you do a log transformation, it makes the data less scrutable. And this is an unsupervised analysis, so we want to understand. We wanted to use the model so that we could help better understand the nature of the data. Another attribute is that the way that the data was measured meant that some of the attributes didn't have very good high levels of granularity. So that affected our analysis a little bit. If we had wanted to, we maybe could have added noise to the data to make it closer to continuous, but again, we opted to keep the data as close to its original state as possible. And this is the PCA transformed visualization of our clusters that we got. So as you can see, they're not terribly well defined or separable. We did pretty consistently get one cluster to the right, one in the middle, and one on the left. To make these plausible, you would have to come into the data with a strong belief that the Gaussian model was appropriate and using that they did fall into clusters defined by normal distribution. For example, we used k-means also just to compare, and you can see much tighter clusters with k-means. So if that was your goal, then k-means might have been more appropriate. Again, it kind of just comes down to your theory with regards to the data, and should the data be determined by normal distributions. If you believe that that is the case, then Gaussian mixed models would probably be more appropriate than k-means, but k-means is definitely superior at finding smaller and tighter clusters. When we looked at the clusters to see the differences, we did see some salient trends. We saw that clusters 1 and 3, which appeared in the left in our visualization, were consistently greener and farther from industrial features, and they were also less expensive, whereas clusters 2 and 4 were more expensive and were closer to industrial areas. So that was the clustering analysis was able to take away that information from the data. We were somewhat disappointed that we weren't able to see interactions between the clusters very well. We didn't get anything like very green but also expensive, or very green but also close to markets. The clusters just didn't have that level of granularity for yeah. So overall, we weren't terribly satisfied with the results of the Gaussian mixed models. I'm not sure that this is an entirely appropriate application of them. A big factor was very slow runtime. We had to sample much smaller subsets of our data, roughly 5 to 10,000 cases. In order for our runtime to be slower than, say, 10 minutes, we also couldn't select more than 5 to 7 columns in any given case. And this is problematic, partially because Gaussian mixed models are very sensitive to kernel selection. So you have to either come in knowing what the kernel should be, or you have to you'll get highly different results every time. So it takes a lot of running the model and tuning the parameters in order to get it to settle on something. And again, like the visualization showed, there's poor intergroup and similarity, and the clusters were quite spread. So we would say that housing market data probably isn't a great application of Gaussian mixed models. A lot of the more successful applications use them in fields where you have prior knowledge of what the distribution should look like from theory. So something where you know that it's going to look like a wave, such as light or noise data, that would probably be more appropriate than housing data, where you don't really come in with any prior assumptions with how the data should look like. And yeah, and this is just a demonstration of how sensitive the data can be for kernel, even with relatively well-defined and that is the end of my presentation. Thank you so much.